So in this video, what I want to do is to discuss changing variables in integrals of one variable. And the key formula that we use is this formula here, which is the integral formula which is familiar from integration by substitution. But here we're being much more active. So the process that we're following is we look at our initial integrand and we think about trying to rewrite it in terms of a new variable, which here I'm calling u, and we write our old variable, here x, in terms of the new variable. And I'm going to be looking at explicit examples in this video to do with tangent substitutions, but the basic techniques that we're going to discuss are valid for many other substitutions. So what we do is we take our initial integrand and we write this in terms of the new variable. So I'm going to be doing an example on the next slide, but essentially we rewrite x in terms of our new variable u, and then we write the integrand in terms of it. We also calculate the derivative dx du in terms of our new variable. So x is expressed in terms of u, we differentiate it with respect to u, so we have again a function of u. We multiply our integrand written in terms of our new variable by this derivative, and then this product is our new integrand, and we integrate with respect to our new variable u if we are able to do it. So again, as always in integration, it's not guaranteed that it will work, but it may be, if we think of a clever variable to use, that we're going to be able to perform the integral. So what I want to do in this is to present a few examples where tangent substitutions are used, but I emphasize again the general techniques that we're talking about can be applied to different integrals. So let's look at an example on the next slide. So the example that I want to look at first is this integral here, the integral with respect to x of 1 over 1 plus x squared. Now 1 plus x squared is always positive, it's always greater than or equal to 1, so this cannot be factorized. So it is also a standard integral, and you may well recognize it and know that this integral is equal to the arctangent of x plus some integration constant. Now you can show that this is true by differentiating this using implicit differentiation and showing that it yields this integrand, but what I want to do now is to actually use this as a simple example, a relatively simple example of changing variables in an integral to show that we can get from this integral to this result. So instead of differentiating and going backwards, we're going to try to integrate this and go forwards. And the key fact that we're going to use is that if an integrand involves a factor of 1 plus x squared or the square root of 1 plus x squared, a tangent substitution may be useful. So let's just note for future use, if an integrand contains 1 plus x squared or the square root of 1 plus x squared, then a tangent substitution may be useful. So this is the key fact that we're going to be using repeatedly through this video. So let's look at our example and let's think what a tangent substitution means. So we say that x, the variable that we have here, is equal to the tangent of u. This isn't putting any restrictions upon x. X can be any real number in this integral. It can be from anywhere between minus to plus infinity, and of course the tangent is also unbounded. So the tangent of an angle can be anywhere between plus and minus infinity. So that's perfectly allowed and does not restrict us in any way. We're going to need dx du, so we might as well calculate it immediately. Dx du is sec squared of u, so that's a useful thing that we're going to have. And we also want to look at our integrand, 1 over 1 plus x squared. So also the integrand 1 over 1 plus x squared is 1 over 1 plus tan squared of u. And now we recall that 1 plus tan squared u is sec squared u. So what we have here is 1 over sec squared of u. And now we use our formula. So now we recall from the first slide the change of variable formula. And the change of variable formula says that if you have some integral, f of some variable that I'm calling x integrated with respect to x, you can rewrite your variable x in terms of a new variable u. You multiply by dx du, and you integrate with respect to your new variable u. So in the context of our example here, what we have is that our integral is the integral of, so first of all, 1 over 1 plus x squared, which we have just said is 1 over sec squared u. So this is 1 over sec squared u. We then have to insert by hand a factor of dx du, and dx du we have just said is sec squared u, and then we integrate this with respect to our new variable u. When we look at this, we see that there is a lovely simplification, and the simplification, of course, is that the sec squared on the top and the sec squared on the bottom cancel, and we are left overall just with 1. And the integral of 1 with respect to u is just going to be u. Now, if x is the tangent of u, u is the inverse tangent of x. So therefore, our integral is going to be tan to the minus 1, or arctan, of x plus an integration constant. And that is just the result that we recall at the bottom, which you can obtain through implicit differentiation. So this has been an example of changing variables in an integral, and let's look at it now carefully to see how it worked. So we started off with an integrand. We spotted that our integrand has a factor of 1 plus x squared, or a factor of the square root of 1 plus x squared. You can think of this as the square root of 1 plus x squared all squared. And because of that, we thought a tangent substitution might be useful. The reason that it's useful is because in terms of x equals tan u, 1 plus x squared, which is 1 plus tan squared, can be written as sec squared u. And that means that it may be possible to calculate an integral over this with respect to u. We have to insert this factor by hand, and that made this particular integral extremely simple because these two factors cancelled. But obviously sometimes these factors won't cancel, and we're going to have to perform a trigonometric integral over trigonometric functions of u. So we'll look at that, or an example of that, on the next slide. So the second example that I want to look at is the integral with respect to x of 1 over 1 plus x squared to the power of 3 halves. So we notice again that the integrand contains a factor of the square root of 1 plus x squared. It contains 1 plus x squared, square root of it, all cubed. So therefore it is logical to think, let's try change of variables, and our change of variables is going to be that x is equal to the tangent of u. So let's again recall our formula, that the integral of some function of x with respect to x is equal to the integral of the same function but x expressed in terms of some new variable, that we insert by hand the derivative of x with respect to the new variable, and then we integrate with respect to the new variable. So here our integrand is going to be 1 over 1 plus x squared to the 3 halves, and that is 1 over, and it's 1 plus tan squared to the 3 halves, and 1 plus tan squared, as we've just said a moment ago, is sec squared of u, all to the 3 halves. And that is going to be 1 over sec of u cubed. The other factor we're going to need is the derivative of x with respect to u. So that means we need the derivative with respect to u of the tangent of u, and that is sec squared of u. So now we have all of the ingredients that we need to substitute into our formula. We have the integrand written in terms of our new variable. This was the integrand, and in terms of our new variable, this is it. And we have the derivative written in terms of our new variable here. So all we do is we take this, multiply it by this, put it in here, and integrate with respect to our new variable. So what we're going to have is that I, our integral, is the integral of 1 over sec cubed of u multiplied by sec squared of u integrated with respect to u. And we see immediately that 2 powers of sec will cancel with 1 power here, so this is going to give us the integral of 1 over sec of u with respect to u. But sec of u means 1 over cos of u, so if we have sec of u in the denominator as we do here, this is just equal to the integral of the cosine of u with respect to u. And that's therefore a very simple integral, and what we see is that our integral I is the sine of u, you differentiate sine, you get cosine, plus an integration constant. So this substitution has been a good one, because with it we've been able to rewrite our integral in this way, and having done that we found out that it's yielded an integral which we've been able to calculate. So again, these factors of 1 plus x squared in an integrand, it's helpful to make a tangent substitution because this is quite simple. It can become this, and then we might be able to, obviously not always, but we might be able to perform the integral, and in this case we've been able to do it. So our integral is the sine of u plus an integration constant. Now, this is all very good as far as it goes, but what we would like to do is to write our indefinite integral here in terms of our original variable x. Now, x is the tangent of u, and that means that u is the arctangent of x, and we could put that in here, but that is, to be absolutely frank, pretty horrible. The sine of the arctangent of u is not a nice looking thing. So instead of that, we really want to write it in a nicer way, and the way that I'd like to do that is based upon simply drawing a triangle. So I'm going to make a bit of room, draw a triangle, and let's see what I mean. So let me draw a right angle triangle, and everything that I do is going to be more general than just having an angle in the first quadrant, but we'll work this way for the moment. So if we're saying that x is the tangent of u, it means that u is an angle. So let's say that in our triangle this angle here is u. The tangent of this angle, and I'm drawing here a right angle triangle, so the tangent of the angle is this side divided by this side. And we want this ratio to be x. Now obviously there are infinitely many values that you could choose here, but the simplest value is to say that this side here is x, and then you would say that this side here is going to be 1. And with that choice, x here and 1 here, it is clear that the tangent of u is equal to x. From Pythagoras' theorem, we know what this side is here. This side is the square root of 1 plus x squared. And this obeys Pythagoras' theorem. The square of this is 1 plus x squared, the square of this is 1, the square of this is x squared. You add the two together, so the sum of these two squares is the square of the hypotenuse, Pythagoras' theorem. So, if you draw a triangle like this, it is straightforward to rewrite things like the sine of u in terms of our new variable. So the sine, or rather in terms of our old variable, the sine of u is this side divided by the hypotenuse. So from the triangle it is going to be x divided by the square root of 1 plus x squared. So therefore what we see is that the integral with respect to x of 1 plus x squared to the 3 halves is equal to the sine of u, which is x divided by the square root of 1 plus x squared, all plus an integration constant. And that is our result for the definite integral, and I would encourage you to check that it is correct by differentiating our result for the integral. So we want to check this. I'm not going to do it, but I very much encourage you to do it. Differentiate this and show that it produces the original integrand 1 divided by 1 plus x squared to the 3 halves. So again, let's look briefly at this integral again. We saw in the integrand that there was a factor of 1 plus x squared to the power of 3 halves. So we thought it might be possible to do this integral using a tangent substitution. This is the change of variables formula we use. We rewrote the integrand in terms of our variable. We could have at this stage already written this as cos cubed of u. We didn't, but that's a matter of taste. We also need, for this formula, a factor of dx du. X is the tangent of u, so we immediately differentiated this, found our factor of sec squared u, and that's the other factor that we need to put into this formula here. So we multiplied our integrand by this derivative. This gave us our new overall integrand, and it turned out to be relatively simple, and we were able to integrate it with respect to our new variable u. So our integral turns out to be this in terms of our new variable, but we wanted to write it in terms of our old variable x. And to do that, I've introduced this idea of a triangle, that if x is the tangent of u, you say that the tangent of u is going to be x over 1, and this side, the hypotenuse, is the square root of 1 plus x squared, and that lets us write the sine of u. And as I said, the way to check if this is correct or not is to differentiate it and see indeed that it is. So I'd just like to move on to one final thing on the next slide. So what I want to do to finish this video is I want to look at the first example again, and I want to do it in an incorrect way. I want to use a substitution that's not going to work very easily. So supposing we look at our integral and we see we have this factor of 1 plus x squared, and let's imagine that we say to ourselves, let's try a different substitution. Let's say that x is the sine of u. And that means that dx du is the cosine of u. Now, this is a perfectly good substitution which works for some integrals, but it does not work for integrals with factors of 1 plus x squared in them normally. So let's see why not. Our formula, our key formula, is on the page before. So we are using that the integral of some function of x with respect to x is the integral of our function with x written in terms of a new variable and then multiplied by the derivative in terms of the new variable and integrated with respect to the new variable. If x is sine of u, then 1 plus x squared is 1 plus sine squared u. And that means that our integral is going to be the integral of 1 over, and now we're writing 1 plus x squared in terms of our new variable, so this is here 1 plus sine squared u. We put in a factor of the cosine of u by hand, that's this factor here, and we integrate with respect to u. And the point is that this has now not simplified. Our factor of 1 plus x squared simplified nicely when we said that x was the tangent of u, but when we say that x is the sine of u, this does not become simple. So this is not easy to integrate. So it is not a very helpful substitution. So another way of looking at this is to draw the triangle just as I did a moment before. So let me just pause and make some room. So let's draw a triangle, a right angle triangle again. Just as before, if we say that x is the sine of u, it means that u is an angle. So let's say that this is u. And if x is the sine of u, that means that the sine is this side divided by this side, and the simplest set of choices are to say that this is x and this, the hypotenuse, is 1, because therefore the sine of u is this divided by this. And that means that this side here is the square root of 1 minus x squared from Pythagoras' theorem. The square of this is 1 minus x squared. You add to it the square of this, x squared. The x squared and the minus x squared cancel, and you're left with 1, which is the square of 1. So in this case you can see, for example, that the cosine of u would be the square root of 1 minus x squared divided by 1, and you could imagine that an integral with a factor like this, it's going to be easy to write this in terms of the cosine of u, and such integrals are done involving a sine substitution. However, there is no factor of 1 plus x squared, so therefore in a different way we also see that this is unlikely to help. So with that, I'd like to stop this video we've looked at tangent substitutions. We've seen here at the very end that other substitutions also exist, such as sine substitutions, but we've seen how to calculate them, and with that I'll stop the video.